Hey everyone, welcome to the discussion this week. I'm going to start sharing my screen in just a second. All right, here we go. And we should be good. Okay, so today's discussion is on sets, maps, and hash tables. So these are really fun topics. Let's get into it. So today we're going to be talking about hash tables, hash functions, collision, how we deal with collisions in hash tables. And then after that, we're going to talk about sets and then do some example questions. So first of all, what is a hash table? So it's a data structure. So with this data structure, you have data values and then they're mapped to buckets. So maybe you remember this, for example, if you took programming 1, so from Java, maybe you know about hash maps. And so that's, I will see, very similar, or it's kind of an implementation of a hash, right? So the idea is that you have like keys and then they map to buckets which contain values. And generally we have some functions, some hash function, which gets the index in an array of buckets. So if we have, for our hash table, right, we might have some keys and we want to know how we get from the key to the bucket we want. And the way we decide that, the way we, like, if we're going to use a hash map or hash table or whatever, right, if we have some key, right, we want to know, okay, how do we know that we're going to get this exact value that we said we wanted to get, right? If we map like a key to a value, how do we actually get that value? And then that's done is with the hash function. It takes in the key and then spits out the bucket that we want for the value. And the values are placed into the bucket, and that depends on collision resolution policy, which we'll talk about later as well. And hash tables are non-ordered data structures. So that's kind of interesting, right? Because like there's no ordering necessarily. Like you could put them in some order and they may be completely different order when you actually try and get them. So it's like unordered map in C++. And that's because there might be order based on the hash function, for example. That function, like there's no ordering necessarily to it, right? So, and yeah. As we see down here, hash map and hash table are often used interchangeably, but there's a slight difference, right? And it's hash map is unsynchronized and not thread safe. And so, yeah, in a multi-thread environment, you can only have one thread working on hash map at a time, but that's not true with hash tables. They're synchronized, so across threads. Yeah. So this is kind of what a hash function might look like. It might take in John, might spit out the index like 3, for example, and Lisa might map to index 2, and then it has a value in its bucket, right? Okay, so let's get into the details because this is just like a high-level overview. Maybe it's not so clear yet. So first, we're talking about hash function. So hash function is, again, you pass in the key and it's going to give you the bucket that corresponds to that key, right? So you're just going to give it a key and it's going to give you like a value basically, but there may be many values inside of a bucket, right? So hash function distributes entries across an array. And the two conditions are, these are kind of important, right? The two conditions are that it should be able to evenly distribute the data. So it shouldn't always give like 0, for example. You don't want everything like 0 because then that's not very helpful, right? You want it to evenly distribute across the array you're using, right? Because you want it to be relatively random, which is good, because that means that it wouldn't take very long to access each element because it's only one element in each place in the array, for example, right? And it should also be easy to compute because if it's really hard to compute, that may also take a long time. And the whole idea of hash maps or hash tables are that they should be very fast, right? Not like you want O1 access and insert. And if it's really slow, then that kind of defeats the purpose. So easy to compute and evenly distribute the data. And they shouldn't be random though, because if they're random, then you can't get the same thing every time. Like if I were to insert Bob, for example, I want to be able to insert Bob. And each time I insert it, for example, I want it to be in the same place. Otherwise, how would I be able to search for it, right? So it shouldn't be random. You want to use the same hash function. Same hash function should give the same output. And common hash functions are key mod table size, mid-square hashing, and string hashing. So we'll kind of see a little bit of those. So key mod table size, for example, is if you want to insert, let's say, value 462 into a table of size 10, then you just do 462 mod 10, saving it 2. And so you insert it into index 2. And 1093 mod 10, index 3. So you put it in index 3, right? And 6 mod 10 is just 6, and 491 mod 10 is just 1. So you're just inserting those into those indices in the bucket, right? And that's pretty simple. Key mod table size is pretty simple. Hashing, and it should always give the same thing, right? Because 462 mod 10 will always give the same result. So it's easy to compute. It relatively, it might not evenly distribute data, but it might. So it's probably good in that regard, right? Depends on what your data is, and it's not random. So those are good. So okay, full question number 1. You can pause and try to figure it out. So what index will the potato be if we use the hash function string size mod 10? Okay, well, it's 6, right? Because the length of potato is 6, and so we have string size is 6, mod 10 is just 6, so we would have index 6. Okay, cool. So there's another thing that's important to talk about with hash tables, which is called the load factor. So load factor is the number of elements in the hash table divided by the size of the array. Because if you think about it, with a hash table, right, you might have a hash table of a certain size. And the issue is that, like, let's say we have like a really, like a certain size hash table. And let's say we insert like a bunch of elements, then there might be a problem, right? Because as we said before, we kind of want it to be really fast access. And like, I guess, yeah, let's talk about this then, right? Like one of the good things about hash tables is that they have really fast access. But if let's say we are inserting like 100 elements into this, into all of these buckets, right? There are only 10 slots. Then we're going to be inserting on average like 10 things into each like bucket. But then that means we have to search 10 things for each one. So that kind of defeats the whole purpose, right? Because if you only have 10, for example, and it's just a set size, then on average, we're going through n over 10 for each of these buckets, which is not ideal, because then it's not O1 retrieval, it's ON retrieval, and maybe ON insert as well. So that's not good. So how do we fix that? Well, the way we fix that is actually with using load factor. So the load factor adjusts the size of our hash table, like the size of the number of buckets, so the size of that array of buckets. And it adjusts it based on this load factor, which is how many things we can put in over the size of, or the number of buckets. So it's basically number of things we put in over number of buckets, right? So as the load factor grows, you're gonna have fewer collisions. And a collision is when you try and insert 2 things into the same place in the hash table. And that's slow because if you insert 2 things in the same place, then you have to do collision resolution, which we'll talk about later. But that is a slower process than just inserting, right? Because you actually have to do something extra. So ideally, we don't want things to collide at all. So that's why we have a load factor, because we want to prevent collisions. We don't want 10 things in one slot. So when we insert values into a hash table, we can change the size of the array to maintain that load factor. So that's an example. We have an array of 10 elements. So like we have 10 buckets, for example, we want to maintain a load factor of 0.8. We can increase the size of the array when we insert the 8th element. And as a real world example, there's been a lot of studies into this, and well, that's how Java ended up with a load factor of 0.75. So the default for hash map in Java is a 75% or 0.75 load factor. And of course, when you actually have to deal with the load factor, like when it gets past that 0.8 or 0.75 or whatever, you have to actually like increase the size of your array. And so doing that, of course, takes time. So you don't want to keep doing that every single time you insert something. That's why you want it to be relatively large, but you don't want it to be too large, or you're never going to actually change the size of the array. So that's why you need a good trade-off. And that's why they chose 0.75. They found that to be a good trade-off. Okay. So, all right. Question number 2. I want to maintain a load factor of 0.5 and have an array of current capacity of 20. When do we increase the capacity of the array? Well, okay. So actually to find this, it's just the load factor. But yeah, so if you haven't paused, but all right, so I guess we're gonna go over the answer. So if you don't know, then you can just figure out this way. It's the load factor times the capacity, right? Because that's how many things you put in before you need to actually change it again. Because once it goes past the load factor, that's bad. We only want it to go up to the load factor. Once it hits the load factor, we increase the size. We increase the size of the array. So we want to increase the size of the array once we get to 0.5 times 20, right? Which is 10. Because when we hit 10 elements, that's when we actually hit our load factor. And if you notice, 10 is 1/2 of 20, so 0.5 of 20. So at that point, we actually want to increase the size. So this one's going to be B. So yeah, we want to increase capacity when we get to 10 elements. And yeah, we can see here if we increase the capacity when we get to 11 elements, the 11th answer won't be as efficient as the first 10 because the load factor will be larger, right? Or like not, yeah, so that would mean that we'd be using a larger load factor and it would take longer because we'd actually have to, we'd be more likely to have a collision. And a collision means we have to use our collision resistant solution, which is not something we want to have to use or want to use as infrequently as possible. Okay, so what do we do to resolve collisions? So when you insert an element, there are a couple possibilities, or there is a possibility that a hash function generates an index that's occupied. That's collision. So if I, for example, did like before, let's go back to this example here. Let's say that I inserted 462, and then I also inserted like just 2. Well, both of them are going to be using the bucket 2, right, in our array. I think we're going to try and use this bucket. And so that's a collision. So when we have a collision, we have a couple options for how we want to resolve them. We'll talk about them. But the very first, yeah, so here, yeah, this example is the same, right? 462, 92 in a hash table came out 10. They're both going to go in index 2. And so we have to decide how to implement it. Probably the most basic way to implement it is just don't allow there to be collisions with keys. So if you try and put in 92, and there's already 462 in there, just don't allow it. Obviously, that's not very helpful because, I mean, a user is not going to like that very much, right? So that's not a good approach. I mean, it will work, but it won't allow them to exist at all, which is probably not very good. So you can allow collisions, and then there are 2 options. One is called open addressing, the other one's separate chaining. And so we'll look at them. First one we're going to look at is open addressing. So open addressing, all entry records are stored in the bucket itself. And when you perform an operation and the hash function provides a collision, so when there's a collision, we try and perform the operation. And so, for example, if there's 462, we try and put in 462. And then if we try and insert 92, we try and insert 92 in the same space. But how do we do that? Like, obviously, we can't put them in the same place. What happens if there actually is a collision, right? Well, there are a couple open addressing schemes. One is linear probing. You can look for the next immediate spot. So if we have, let's say just, I don't know, I'm just going to look at the first 3 spots, or I guess first 4, right? 0, 1, 2, 3. And there are more later on. Let's say there are 10 total. And we try and enter 462 and 92, for example, right? Then there 462 is going to be the first one inside of 2, right? 462. And then, well, one option is to use linear probing. So we look at the next open slot and if it's empty, we put the thing in there. So here, 92 conflicts, there's a collision. So we might put 92 in index 3. So yeah, so if there's already a value in it, we look at the next index, and the next index, and the next index, and the next index, until we find an empty spot. So here, 462, let's say 3 was full. And so we can't put 92 there either. So we have to look at the next one. Maybe that's empty, so put 92 there. Otherwise, we're gonna have to keep looking. And we don't have to look forever as long as the load factor is less than 1, right? Because if the load factor is less than 1, then that would mean that we never actually fill the array completely. Like we never have all the buckets full. So as long as we have less than that, then we'll always be able to find the slot. Just might take a while. Another option is quadratic probing. So we, instead of just checking the interval between them to be 1, right? Instead of just going, okay, 2, let's check 3, let's check 4. Maybe you check 2, then 3, then 7. And then you check, I guess, 16, but if 16, if it's only size 10, we take maybe like 10 or 16 mod 10. So then we check like 6. And then we check 16 plus 6 is 2, for example. And this helps us get out of like clusters, which we'll see is a problem. But this is an option. You can use quadratic probing. So instead of going 1 by 1, you can go like 1, up by 1, up by 4, up by 9, up by 16, and so on. So if index 6 already has a value in it, we could look at index 7, then index 10, then 15, 22, and so on. Okay, so let's go through an example. I think this is going to help if you're a little confused. So we want to insert the values into the array using the hash function, string size, mod, array size. And the array size, let's say, is 10. We also want to maintain a balance factor of 0.7. So if we're using linear probing, remember that just goes 1 by 1, right? It's kind of like linear search, right? Linear search, if you remember, like you go 1 by 1. Here, linear probing again, you're just going 1 by 1. Okay, so originally the load factor is 0, so we don't need to actually increase the size of our array. And the first thing we want to do is we want to put Josh in there. So Josh is at length 4, right? So we just put it in 4, mod 10 is 4. So you just insert it in 4, and we're good. Okay, so what's next? Well, we want to put DOM. Well, DOM is of length 3, right? So 3 mod 10 is 3, and we put in position 3. And we're still load factor is just 0.2, so less than 0.7, and so we keep going. Next one's Katie. Katie's length 5, right? So we'd want to put Katie in 5, and then our load factor would go up to 0.3, and we still wouldn't have a problem. We'd have no collisions, and our load factor would be less than our load factor would be less than the balance factor, which is 7. So far, so good. Then we have Sabrina, and Sabrina is now in position 7, right? Because her name is length 7, so 7, still no problems. Then we try Jonathan. Jonathan is of length 8, I believe, yeah. And load factor is still less than balance factor, so we're still good. Then we insert Tima. And with Tima, we have a collision because it's a length 4. So we try and insert it. There's something in there. So we try the next index. So we would do Tima and Josh. So our Tima and Josh are both trying to go there. We use linear probing. So we try 4. 4 doesn't work. We try 5. We try and insert at 5. That doesn't work either. Sorry, something there. So now we try the next spot, which is 6. And it's empty. So we insert there. And we're done with Tima. And the load factor is only 0.6, less than 0.7. So we can move on. So we try Drew. Now Drew, where does Drew get inserted? It's a question for you. You can pause and try and figure it out. Now I'm going to go over the answer. So Drew, right, is of length 5. So 5 mod 10 is just 5. So we try and insert here where Katie is. But that's conflict, or that's collision, right? So we try to the next one because we're still using linear probing. So go to the next one. And there's a collision here too, right? So we can't do that. Try it 6, no good. Try it 7, no good. Try it 8, no good. Try it 9, and we are good because there's nothing at 9. So we can actually do that. So we would insert a position 9. If you said 9, good job. If you didn't, that's okay too. Hopefully you learned this. But now we've also reached the load factor of 0.7, right? Our balance factor and load factor are the same. And so we need to expand the array. So when we do that, a lot of times that just means multiplying the size of the array by 2. And then, yeah, just going from there. So we double the size of the array. And now our load factor is only 0.35, right? And it's only 0.35 because we only have 7 over 20. Okay. And now we try and insert a MAR. And a MAR gets inserted in what index? So this is a whole question here as well. At index 10. Yeah, so I guess I should have said pause, then we'll answer, whatever. Hopefully, yeah, that's about it. So yeah, and the reason why it's 10 is we try to insert it at 4, right? No good. 5, no good. 6, no good. 7, no good. 8, no good. 9, no good. Finally, 10 is okay. So that's where we insert it. And so you might notice that there's a problem with linear probing, which you know is clustering. And it's and you can maybe see in the buckets below where like they all kind of cluster around one space because you just go 1 by 1. And that can be an issue because you might just keep running into the same kind of cluster where you have to go next, 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 next. And quadratic probing helps fix that. You get out of clusters more quickly. You would have inserted a more at index 4, then 5, then 8, then 13, and so on. So we've gotten that out of there more quickly. But there's another collision resolution policy that we'll talk about instead. That's also a solution to this problem. So to help fix this, as I said, just to reiterate, you could have used quadratic probing, but also another solution to this is separate chaining, which is another approach to collision resolution altogether. And separate chaining is what we'll talk about next. So separate chaining is when we chain elements together. So rather than the buckets being an element each, like instead of, for example, before we had integers, for example, or actually it's strings. For actually, yeah, this example, it's strings. In each bucket, what we can do instead is we can kind of have like a linked list in each bucket. So instead of having just one string, we can have like a linked list of strings, right? So we chain together, like with a linked list, the elements. So each bucket is independent and has a list of entries with that same index. And the time to hash the elements is both the time to find the bucket and the time for the operation. So you might need to find the bucket, then you might need to insert it at the end of that linked list. So, I mean, you might think, okay, well, that takes longer because we can't just insert it. It takes more time than that. But really, it may not be as bad because it takes almost no time to find the bucket. And as long as the load factor is never very large, it's going to be unlikely that, or as long as the load factor is never very large, then all the elements are going to be relatively spread out, hopefully. So you will have very few elements in each list, if any, right? So ideally, you won't have very many each. Okay, so all right, let's look at this. Let's look at this example, right? So let's do the same thing as before. We have our hash function is string size mod array size. So again, we have the load factor 0 at the beginning. We try and insert Josh. So insert Josh. Josh is of length 4, right? So he's going to go in index 4. So we insert him as like a node or like in a linked list, right? At 4. For Dom, we try 3. Okay, so insert it 3. And Katie is of length 5, so insert it 5. Sabrina is of length 7, so we insert it 7. Jonathan is of length 8, so insert it 8. Team is of length 4. And yeah, we already have something at 4, right? And so rather than before, if you remember, what we had to do before is we actually had to go through and find the next empty spot. But here we don't have to do that. Like before, we would have had to have found 4, okay, full, 5 full, oh, 6 is empty, so we would have inserted there. But here, there's no need for that. We inserted 4, and there's something at 4, we just add it to the end of our linked list. So we're like chaining it together, all the things linked 4. Or anything, all the things which mod table size are 4 anyway. So we just add Tima in there at the end of that list. And then we do the next one, which is Drew, and it would be the same thing, right? But at 5. We already have something at 5, so we chain it together at 5. And then we go with Amar. Well, actually, first we have to notice that our load factor is equal to our balance factor. Okay, well, actually, here we didn't have a balance factor. That would have been true in the previous example where we had balance factor is 0.7, but here that's not the case. We're just keeping track of what our load factor is. But anyway, now here we insert Amar at 4 as well, because Amar is length 4, right? And so we just chain him to the end of that list. And so we're good. And yeah, we didn't have, as I said before, the reason why we weren't concerned about this is because we don't have a balance factor that we care about in this example. But if we actually look at it, linear probing with open addressing, right, which was the one we're going 1 by 1, can be pretty good if the load factor is really small. But as the load factor gets bigger, it can be less of a viable option because of the clustering we noticed before. We have to keep checking. That's not good. Chaining remains relatively consistent because even though the chains might get larger with larger load factors, it may not be as much of a problem because at least it doesn't take very long to find them. And they should be evenly spread out across each of the buckets. So this is just kind of, how many misses you're going to have per lookup. on average. Okay, so that covers the collisions. So hopefully that makes some sense. So you guys, if you have questions, you can always ask, like, you can message me on Slack or email or whatever. So C++ map versus unordered map. So map, a C++ map is actually just an ordered map, right? It's ordered. And when we actually create ordered maps, as you guys may notice in your project too, is we just use a tree, a balanced tree, or a balanced binary search tree is how ordered maps are handled. In C++, and in Java for tree maps in C++, or tree maps in Java and maps in C++, they use something known as a red-black tree, which we have covered before, right? And they are just a balanced binary search tree. So ABL trees, you can also create ordered maps with them as well, which is, as I said, what you're doing in your project, right? So that's how maps are. That's what we use for maps, is balanced binary search trees. Ordered maps, that is, unordered maps, we create hash tables or hash maps, and we have dynamic arrays because, as we notice, we have to increase size of the array when the balance factor or the load factor comes too high. And that's how an unordered map works, is with these hash tables that we have been talking about today. And the good thing about those is the operations are just O1, whereas the operations, as we remember from balanced binary search trees, are all log n. So the downside to unordered maps are that they're not sorted. The elements aren't sorted. They don't have a sorted order to them. So if you want to actually access them in sorted order, that's too bad. You might have to go through all of them. But if you just want to access and retrieve, they're great because you can just do all your operations at once, right? Insert, remove, get. So that's the benefit of unordered maps versus ordered maps. Yeah. Okay, so time complexity. So in standard template library, so STL functions, what's the time complexity of performing all hash table unordered map functions? All right, so you can pause, you can try and answer, and now I'll go over the answer. The answer is O1, right? It's O1 on average. We're only expecting one operation, and the other operations you can amortize, but don't worry about that too much. You just know that in general with maps, with unordered maps, operations like insert, delete, and search are just O1. Okay, so if you have any questions this far, of course, you can just let me know. So what we talked about were hash tables and how they work, hash functions, collision resolution policies, and also the computational complexity of hash table implementations. And now we're going to talk about sets. So sets are an abstract data type. So like with queues, like with priority queues, like with heaps, well, I guess just queues, priority queues, stacks, like those are abstract data types, and so are sets. And so the interesting thing about sets are they're collections that don't contain duplicate elements. Sets are not indexed. There's no inherent ordering. They allow membership testing. So find, insert, and remove, and they allow removal. So sets, as you may notice, a lot of the things that sets implement are kind of very closely related with hash tables, right? Where they're not indexed, like there's no ordering. You can have remove, insert, find. And so now we can talk a little more about them. So just based on that information, maybe you can try and figure this out. What's the output of the following code? So it's just a poll question for you guys. You can pause and try and answer this using this code on the right. All right, so now I'm gonna go over it. So to figure this out, right, we go through it and we say, okay, one was inserted into our set. So let's just like use set notation. Scene of one. Then we insert 37 on the next line. And then on the next line, we insert 45. Then we insert 6. And then we insert 37. But remember, sets don't contain duplicates. Sets don't contain duplicates. Sets don't contain duplicates. And then we erase 1. So we're removing this from our set. So at the end, right, well, now that we've removed the 1, we just have 37, 45, and 6 in our set. And so our size is just 3. So we'll have this. Okay. So now we can try and use some problem solving using sets. So let's try and do this. Intersection of two arrays. Given two arrays, write a function that computes their intersection. So as an example, we can look at input. Nums1 is 1, 5, 5, 1. Nums2 is 5, 5. We want to input output 5, which is their intersection. And another example, input is 429, right? And the intersection of 429 and 94489 is just 9 and 4, right? So let's talk about how you could try and solve this. First, you can try and solve it yourself. Then we'll try and solve it, and then we'll go over the code for it. So first, we'll just like first, if you want to try and solve it yourself, go ahead and pause. Otherwise, we'll go over it a little bit, and we'll go over some ideas that you might have, and then we'll actually like look at what the code might look like. Okay. So, okay. So, all right. So maybe you've unpaused, maybe you never paused, and that's okay. So here, what we notice, right, is what we want to do is we kind of want to just get what's in this one, right? What's in this set, what's in this set. And we don't worry, or what's in this array, what's in this array. We aren't too worried about how many times it shows up. Because even 5, though 5, 5 shows up twice here and twice here, we aren't outputting 5, 5, we're just outputting 5. Even though over here, and over here, we just want to get the intersection, right? So 9 and 4 show up in both, but 2 doesn't and 8 does not. So maybe what you might think is like, okay, well, what can we use that allows us to not worry about duplicates and just worry about the elements in the arrays? And so maybe your thought is a set, right? Which is what we're talking about. So maybe what we want to do is we want to look at this first array and we're like, okay, well, we're not worried about duplicates. Let's just put the elements in a set. Let's just figure out what's in the set, or make a set, right? And put the elements in there. So in this one, for example, we might put 1 and 5 in there because that's what our set would be. And because it's really fast to get things from a set, right? Because sets provide insertion and deletion and find. Maybe you're thinking, okay, or maybe actually your first thought is, all right, let's make this set and let's make a set for the other one too, right? And that's a good thought to have, right? So make 2 sets. And then maybe now that we have 2 sets, maybe you want to try and find the intersection of them. So you want to go through maybe, now we have 2 sets, maybe you want to iterate over a set, but it's kind of hard to iterate over a set. You could do it, I guess, with iterators, but maybe instead, now that we have 2 sets, maybe you want to go back to this one because if it's in both the sets, right, it has to be in the first array, right, and the second array. So maybe now you go back to this first array. And you're like, okay, let's go through every element and let's now see if it's in both of these sets. And so that's a perfectly good way to do it. And maybe we could do that for the other one as well, right? But maybe we can think about ways to do that better. And maybe that wasn't so clear, but maybe that gives you some direction of, okay, how can we actually write this? So maybe you can pause now if you want to try and attempt it yourself again. Okay, if I'm paused, I guess what I'll do now is I'm going to kind of go over the answer of how we could think about how to implement this. And then you can figure out how to write the code. And maybe after we've discussed it, you can try writing the code. Or if you don't want to, we can just go over the code right afterwards. So you don't have to pause necessarily. So let's try with this one and this one. And let the same approach, or yeah, the same approach would be just 429, right? And then 9, 4, 8. And so then maybe we go through is 4 in this one, is 2 in this one, is 9 in this one, and is 4 in this one, 2 in this one, 9 in this one. So maybe that's the way to do it. But maybe there's a slightly better way to do this. And the way we're going to do this is we're just going to make a set for the first one. So in this example, input 1 is we're just going to make a set for the first array. We're going to make a set. So we're going to make a set of 1 and 5. And in this lower example, we're going to make a set of 4, 2, and 9. Now, the interesting thing to notice is that, remember, since we're taking the intersection, right, if an element exists in both, if an element exists in both arrays, then it's going to exist in the intersection. Otherwise, it can't. So what that means is that the elements here have to be in this set, right? If they're not in this set, then that won't quite work out for us. So actually, wait, I think on the next slide, we go over some, okay, I'll keep going, I guess. I'll keep going. So what we may notice, there are some other approaches, which we'll go over in the next one, but okay, well, let's just go ahead and finish this up. So what we may notice here is this other array, right? It has to have the elements that are in this set. So what we can do is we can just go through these elements, right? And check if they're in this set. And if they are, then we can add them to like another set or another vector. Well, here we need to return, we're just computing their intersection. So we make another set, right? And if the element is not yet in that set, not in this return set, and it wasn't in this, or if it's not in the return set already, so we haven't already added it to our set, and if it is in our original set, then we can add it to our set. So we go through this array one by one. And we only have to go through the array once, and for each element, we're just checking if it's in this set, and if it's in this set. If it's in this set and it's not in this one, we can add it. So let's try with this example. So if 9 is in this set and not in this one, which it is, we put 9 here. If 4 is in this one, but not in this. If 4 is in here, or 4, now we're on 4. If 4 is in here, but not in here, then we add it. Same thing with the next 4. Well, this 4 is here, but it's already here, so we don't have to add it again. So let me try 8. 8's here, but it's not here, so we don't add it. And then 9 is here, and 9 is here. But 9 is already here, so don't add it either. So at the end, we just use 9 and 4. And we're using sets and original array. So notice we only have to make one pass of this array. We'll make a pass of this array just to make it into a set. But we're going to talk about other ways you might have thought about it. And okay. Or maybe not actually. Okay, we're going to go over the answer now. So here, solution is to use a set. So for every element in nums1, we insert the element into the set S. So this is the first thing we mentioned, right? First thing we mentioned was we're putting all of them from that first array into our set, right? And for every element in nums2, the element exists in our set, remove it from the set, and insert it into the return vector. So this is another approach to it, is we could just remove it from our original set. So what we were discussing was using two sets, but alternatively, if you wanted to return a vector instead of a set, then what you could do is you could just use the remove, right? So you're only inserting once, because remember, okay, well, we'll just keep going. And, well, yeah, and we'll tend to, okay, well, there's nothing else. So then remember that a set only has every element once. So for example, if we had 4, 4, 4 in our first one, and our second one was 4, 4, and actually, I guess let's make this square brackets so we know it's an array. I'm trying to cross that out. Okay. Then our first set is just going to make a 4 as a set. And now when we go through this array, we're going to hit a 4. We're going to like, okay, well, let's input 4 into our return vector. And then let's pop it from here. So now we remove the only 4 from our set from nums1. So when we hit this other 4, now there's nothing in this set that's a 4. So, and there never will be again. So we only actually put 4 into our return vector one time. So this is kind of the approach you could take. And it's similar to the approach we were discussing. And let's look at the code form. So set S, we have our vector to return. We go through nums1. First, we just put everything from nums1 into a set, which will also remove duplicates. And then for every element in nums2, if it exists in the set, we pop the element off the set and insert it into the return vector. So you erase it from your nums1 set. So from this from this set S. And if it's in the set already and it was in nums2 as we're iterating through it, then you insert it into the return vector and you remove it from the set. And then you keep doing that. And then by the end, right, you're going to have every element that was in nums2 and in nums1 inside of your return vector exactly one time. So hopefully that made sense. I know my explanation might have been slightly confusing, so sorry about that. But that's the main idea, and hopefully this code kind of is clear. If you have questions, of course, you can listen. Okay, but this is kind of a use case for sets. They're really cool. Okay, so another example question, and so this example question is given two strings, s and t, write a function determinant t is an anagram of s. So an anagram is a word, phrase, or name from a rearranging the letters of another, such as cinnamon, Iceman, because they have the same letters, right? And the same number of times. And so this question might seem, tricky or weird, but it really is a problem that you might run into. Like my friend actually had an interview just last week with the major company and had this exact question on his interview. So it does come up. So it's a good one to know, have an idea of how to approach. So, okay, maybe you can pause first and take a think about how you might go about this. Now we'll talk a little bit. So let's look at just, some examples. So anagram and grammana, they have the same number of letters, or same number of each letter. So A occurs 3 times in this one, and 3 times in this one. So 3 times for A, 3 times for A. N occurs 1 time in each. G occurs 1 time in each. R 1 time in each. And M 1 time in each. So they're anagrams. They're exactly the same number of letters, same number of each character in both strings. So that's true. But cheese and cheeses is not an anagram because one has one S and has two S's. So even if they're otherwise the same, they're not anagrams. So maybe your first thought even is, okay, well, what about using just a set as we used in the previous question, right? Set for all the characters. But you might also notice that maybe that doesn't quite work out as you wanted it to, because we actually care about how many times each thing comes up. So we care about the fact this one has one S, this one has two S's. So it doesn't quite work that we just say, oh, okay, this one contains an S, this one contains an S, so we're good, because it's not the same number, right? But it's just some assumptions about the problem. String only contains lowercase alphabets, and length of the string is less than 100,000. Maybe you think of an n log n solution. So maybe there are a couple solutions you can think of. So actually, I think the most basic solution you might think of is just, well, let's just go through every letter in this, look for it in here, and like every letter in this, and maybe a brute force solution where you try and find the letter in there on the left one, the letter in the right one, and see if it's one you've already seen before, for example, or already counted. Like you've already counted this A once, this A1 maybe, right? So there's no A here. You want to make sure that you have it. This one has exactly two A's, and this one has 3 A's. This one has 2 A's. You want to be able to like say, okay, I've seen that A before. But that's kind of slow if you go through this one, and for every letter in this one, you go through every letter in this one. That could be slow. The brute force solution could work. But if you think about that, that would be for every letter of this, we go through every letter of this. So maybe that's O of n times m. So maybe that's not ideal. But maybe there's another approach, which is an log n solution. So if you think, there's a way to do that. So let's go to the next slide and let's see kind of how you might have approached it. Okay, actually, wait, that's the solution. So yes, maybe your n log n approach is to think of a solution in which maybe you sort them, right? Maybe you sort the strings. And that's an n log n approach, and that's a good approach. But maybe that's not ideal either. Maybe you're sorting this, right? And sorting this. And of course, if it's sorted, or like sorting all the characters in it. And if you sort all of them, absolutely, it'll give you the same thing because all the A's will be the beginning of one, all the A's will be the beginning of the other, and then all the G's, then all the N's, then R, the M's, no, M, then N, sorry, and then R. So, okay, yeah, so if you sort all the characters, absolutely, that'll give you it should give you the same string, and if it doesn't, they're not anagrams. So that's a viable approach. Maybe there's something even better that we've based on something we talked about today. And so that would be using, maybe you can try and think about it. Okay, so that would be using hash maps, right? Because if you think about it, what is a hash map for? Well, in a hash map, if you remember, you can map like something to something else, and it's O1 for insertion, O1 for retrieval, O1 for removal, which is really nice. So for example, maybe I want to find the number of times that each character exists in each of the two strings. So I would map, for example, I could iterate over this first string. Well, first I would check two strings of the same length. So that would be O1 time. And then I might say, okay, iterate over the first string. And for every character, map it to the number of times we've seen it so far. So for A, I would originally map A to 1. And then I would keep going and map A to. Now I would figure out if A is in my map yet or not. If it already is, I would increment it. If it's not, I would input it at 1. So this is how we go through. So A maps to 1. Then I see N maps to 1. A is already in there, so now A maps to 2. So to see if it's already in there, it's just O1 time. To update it, it's also O1 time. So it's O1 for every letter in the first string. And the two strings have to be the same length. These already checked that. So it's O1 times N plus O1 times N. So that's just ON plus ON. And that's O2N, which is ON. So that's why this approach is really good, right? These only take one time. But let's just go through the rest of this one. So G now, G we've seen 1 time, R 1 time. A now we've seen 3 times. And M we've seen 1 time. And for the other one, G, we've seen 1 time, R 1 time, A 1 time, M once, A again, we increment 2, and 1 time, and A now we're incrementing this one to 3. And now we can't just say, oh, are the two maps equal? Because we can't really do that. What we could do now is we could then go through and see if for every character in this original string, or in both these strings, right, see if they exist the same number of times in each map. So now, for example, what we could do, we could use 2 maps actually, so this is an approach. But yeah, so we could use these 2 maps, and then, for example, we could just iterate over the, so there's another approach we could actually do to slightly improve this, which I'll talk about in a second. What we could do now is we could go over each of these 2, and we could try and now go over this map and make sure it actually matches up. And go over this map and actually make sure it matches up. And maybe a way of going about that even, which is, I guess, the improvement, but is the way going about it. So we can actually just go through this map, and for every letter we see, we can decrement, right? So if we see, like, we can use the second map on the first string, for example, and decrement. So maybe we see an A, so decrement this to 2. And if anything goes negative, then it happens more time in the first string than the second. So that's kind of approach we could use. And then at the end, we go through and see if any of them occur, any of them are still greater than 0, which means it occurs more in the second one than the first one. So that's kind of an idea. Hopefully that's not confusing. But the main idea, and we'll go over like more implementation details in a second. The main idea for the optimal solution would be to use hash map, as we saw. Okay, we're just discussing the solution. So again, could use brute force, or we can implement an ON log n using sorting. So sort both the strings in alphabetical order, go through each of the strings, 1 character at a time, and return false if the characters don't match. We do better, yes, using a hash map, right? And so the actual implementation is here. So we'll use a hash table or hash map. So go through the string S, and for every character in the string, increment a counter in the hash table. Go through every string T. I'll go through the string T, so the second string, and for every character in the string, decrement a counter in the hash table. So this is like what we were talking about, right? With incrementing the first one and decrementing it again, right? And if we've reached a case where the count at the index is less than 0, return false, because that would mean that it occurred more times in T than it occurred in S, right? And then, yeah, that, and the only, yeah, and so this is absolutely what I'm about it, right? Is we go through, yeah, and they have to be the same length. Okay, yeah, as long as we make this, if they're the same length, check, we're good. And interestingly, this is all we need, because if, as long as, yeah, it has to exist in the table. Like, for example, if a character in T doesn't exist in the table at all, they can't be anagrams. So if at any point when we're looping through T, is if, so we're checking if it's less than 0, but if it never exists in the table, that'll also fail, right? So that'll also return. So basically that's how we go about it, is we go through and we're just inserting all of the characters in the first string into a table. And then in the second string, for the second string, we go through every one of them. We check if it's in the table, we decrement. And if it ever hits less than 0, that must mean that that character occurred more times in T than in S, because, well, we subtracted more than we added, right? So, cool. So that makes sense to all of you. And that's it. So that's the solution to this example. Hope it made sense. If not, of course, mess with me. And yeah, that's about it. These are extra resources. Remind you have a quiz. And thank you all for watching. I appreciate it. Have a nice day. Bye.